rotational motion can be linked to linear motion or can be related to linear motion. In a straight line, we can define two positions, x1 and x2. Similarly, in rotational motion, here A and B are positions. We know that the circle has a constant radius, so it means the distance from there is the same. Now, if an object is moving in a circular path, you will actually be altering theta, which is the angle between position A and B. Okay? So in angular or in rotational motion, we therefore use theta as our position instead of your x1 and x2. That's why rotational motion is therefore synonymous with angular motion. We can then say S, which is the displacement, will be the change in x here, which otherwise you've always been saying x2 minus x1. So this is now the displacement. Okay? And similarly, the displacement that side will be given by theta B minus theta A. So this is linear displacement, and this is angular displacement. Okay, remember this is displacement. You know that linear velocity, S over T. This is basically the average velocity. In angular space, V, we use omega. So this is the formula for angular velocity. Let's just make an example of a car wheel. If you've got two positions, the inside of the rim and the outside of the rim, and the wheel is rotating, angular velocity will be made by the change in angle over the change in time. If these were two runners, and one was on the outside track and the other one is in the inside track, then I'm asking you, in order for you to finish at the same time, to complete the revolution, should you be running at the same speed? And we all know that that can't be the case, which simply means that there's a relationship between how fast you have to go around the circle to complete the revolution and the radius. And the equation then that joins the two, I gave it to you as V, which is the linear velocity, is related to omega, which is the rotational or angular velocity, by multiplying that with R, where R is the radius. Now we can easily then see on the picture above that RA and RB are different. And that will actually result in different linear velocity. The angular velocity will still be the same because you're changing the angle in the same way. You're both covering 360 degrees, isn't it? But in terms of the speed, which is now the distance over time, you can see that the person in the outside will have to run faster because his path is longer. And this last equation here compares the two. It compares the linear velocity and the angular velocity. In this example, if, let's say, RA is equal to, let's say, 6 meters, and I'm gonna say RB, which is the smaller one, is equal to 4 meters, right? Now, let's check the velocity that each of them has to use in order to complete a full revolution. So now we're going to calculate their individual linear speeds. VA will be the same as angular velocity A multiplied by the radius of A. 2 pi divided by the time. And we've just given the time there as, let me just say T is equal to 5 seconds. Multiplied by your RA is given as 6 meters. So now you can get your answer here in meters per second. So what is the answer there?
7.5.
So the first one will be 7.5. So you can do the same exercise for when the radius is 4 meters. Just calculate that, and anyone who's finished doing the second part can tell me the answer as well.
5.0.
5.0. So do you see that the smaller the radius, the less the speed? If you're going around a small circle for 360 degrees, you can just go slower than a person who's got to cover a larger circumference.
So why do we use 2 pi?
Yes. Somebody can answer that, please. Why do we use 2 pi, not 180?
Because we did a full circle, not the half.
Yep, that's true. We went through the entire revolution. So the entire revolution is 2 pi, which is the same as 180. But now the angle is in radians. Okay? Why do we use 2 pi, not 180?
Because we did a full circle, not the half.
Yep, that's true. We went through the entire revolution. So the entire revolution is 2 pi, which is the same as 180. But now the angle is in radians.